Okay, so we went through this deflection stuff. I was mentioning there's a lot of different ways to do this. They all tend to be fairly difficult if you do the calculations. Um, Probably the most fundamental way is that integral approach. But there is a way that more sensible people do this stuff, and that's with tables. So I've just handed them out here in class. So I think everybody has a copy. And they're available online too. In Moodle, I should say. So, okay, so you could get them in Moodle under the downloads. They're deflection tables or something like that. So, structural's pretty high liability stuff. And so my thinking these days, now I don't know, I'm not really a structural engineer. I've done a little bit of it, but not a whole lot. But I think if it was really a complicated one, if I were working in industry these days, I'd probably do it on software. There's an awful lot of structural software out there these days that people use. So that's probably how I'd go about it. And if it was simpler and I was in a little bit of a rush, I'd just knock them out using these tables. I can't imagine somebody in industry going through a page of calculus to find deflections. It's just, it's just a bit much. So my guess is it's either be software or the tables in industry. Now in school, it's a whole other deal. I mean, there's 4 or 5 different ways to do deflections. And as I say, if you're doing calculations, they're all complicated. So I wanted to give you that calculus one just so you'd have an idea of kind of where this stuff comes from. And, you might have something next year where you have to do that. But I think a more practical way to do most of these is tables. So this is how I would encourage you to do them. There's some tricks you have to learn to use these things, but the basics of it's pretty simple. They're kind of like the centroid tables, and the moment of inertia tables. You don't have to be doing calculus every time you want to find one of these things. There's standard cases that come up often, and so they get you the formulas for standard cases on a table, so you don't have to do all the calculus, okay? So you'll get one of these when you take the final. So, and I would very strongly encourage you to do it this way. I mean, the calculus is just, it's pretty obvious what it is. I mean, so this is much more straightforward, but you do have to learn the nuances of using the tables, okay? So first thing is first thing I would call your attention to is this is a draft. Basically, I've got a little statement down at the bottom says if you want a really good one, go look at a textbook, okay? This is just kind of what it is. This is for our class. There's plenty of good tables available out there on the internet and in books and all that sort of thing. So, we'll use this for class, but I wouldn't use it anywhere else, okay? All right, now there's 2 sides to this. One side is simply supported beams, and then the other side is cantilevers, okay? So, there's two of them. And I had a little copier problem. Some of you I handed out 2 copies to, and I think they're sorted right. You got one of each, I hope, So there you go. Okay, so that's the cases. So all you really have to do then is just plug in to the tables for the simpler cases. And if you've got 2 cases in one problem, you just find each one independently and add up the results, okay? The one thing on this when you're doing English is remember to watch your units. And generally what that means is pounds for load and importantly inches for length. You don't want to be finding deflections in feet. They're not going to be that big. We would strongly hope they wouldn't be anyway. If they are, something's probably broke. Okay, so get everything into inches, lengths, and also importantly, people often forget this, loads per unit length, like that 3 kips per foot. You'd want to get that into so many pounds per inch is what you'd want to do, okay? So just be careful to get all the conversions made. So what I've done here, these things involve I and E. We got a simple rectangular beam, so we've got I here. We've got E, that's the standard E for steel in the English system. for the mild structural steel that we use. But what we've got here is we got kips. Now kips mean 1,000 pounds is what they mean. And I think I'm on 915. I think this number's still good, but I mean, maybe not. I don't know. I've changed the numbers on it.
Mine's 900.
Okay, that sounds about right. Yeah, this is 900, I think. So we got 3 kips per foot, and then we've got 4 kips on the end. So why don't you start off by getting that converted? Everything is pounds and inches. So why don't you do that real quick here? These are getting all on Friday, so let's work on what's changed. You know, getting that, so I got 96 inches is the length, 250 pounds per inch, and then 4,000 pounds. Okay, we're good with that? Okay. And then the next thing you'd want to do then would be, if we're good with that, is just pick those 2 cases to use. Okay, so look at your table. Just be real sure that you're on the cantilever side, okay? Because that's the side that you would use. And then look at that loading. It's, you know, we got a support on the left, a cantilever there on the right. So pick out both the 2 loads that would represent that. And there's no fancy interactions between the loads. You just add them together is all you do. So you could, you know, find the net angle, which is also a slope, because remember, a slope and an angle in radians are pretty much equivalent, as long as it's a small slope. And then find the delta there at the end of the beam. And, you know, I actually remember a friend of mine's an architect, and he had this big house project, he's down in California by the ocean, so it was his house that kind of had a nice porch that extended out over the ocean on the beach and all that. And, he called me once because he was a little worried that that end of the porch might be kind of sagging down when there was a party, I don't know, it was outdoor. And looked at that just a little bit, so this is kind of similar to that. I mean, what you've got here is a uniform load, that would be the weight of the structure itself, which is generally a uniform load. And then you've got all people on the rail looking over the beach or something that would like, you know, they just don't look at it. It's fairly straightforward thing to do. Yeah, I remember, thought I'd answer something on that one. Okay, he was down. He had a big party after that, just wealthy people, of course. So, they had a big party when the house got built. He was the guest of honor, so he was down in Hollywood there running around at this party. You know. He's a great architect, you know, so he was pretty happy about that. One good thing about architecture, right up there, some pretty good roads that nobody can ever throw a party for me. But I was happy with him. He was there with me laughing about the whole party thing. Some Hollywood types there that were making quite a fuss over him and all that. I like that, you know.
Darn, that must be real hard to get used to.
Yeah, I think it is. He doesn't quite do that stuff coincidentally. He always kind of shifted when he does. But yeah, I think he got a hard time getting used to all that stuff at the party and all that. I'm sure it's hard for him. Especially me, So I don't know, maybe we can change fields if it bothers you. You go down and do along architecture, but that's a whole different way of thinking. I'll worry about that. Architecture. It's like, you do things called plot plans, you know. I'm a kind of engineer. I've done some surveying a little bit and stuff, so, you know, if I do a plot plan, what I'm thinking about is getting the water off the lot, you know. So you got a lot, and you got, whatever you got. At some point when you do these like houses and stuff, you know, you have the lot here. You're going to have the house, you know, whatever it looks like over here. And then you got to figure out the elevations and the grading just to make sure the water doesn't go in their basement or in their crawl space, you know, and you got to grade it and put the fill in the lot so that the water all drains away. And you know, you look at a few other things, you know, and you do a few calculations just to be sure you get enough grade to get the water off and all that. You know, an architect's idea of a plot plan is more like, you know, this is a really cool bush over here. Let's curve the sidewalk. That would be really cool, wouldn't it? And then we'll put some hedges back here and a Roman statue right about there. And they'll do a couple X's. They'll give you a couple elevations, you know, and it's like, come on, man. You want me to build this thing or what? So this is a whole different thing. They think different. Do what you told them. Yeah. This one be super pretty. Yeah, right, yeah.
The architect spec'd out metal roofing for a soffit, and it took a 300 or 400 pound steam roller to put the roofing on. I was like, you can have a guy hold that. So.
You get these projects done somehow, well. You disagree with small. They do a bit of it, you know, if it's serious structural, don't hire a structural engineer. So if architects kind of oversee really the whole project, at least for a lot of buildings. They there's the electric side, but there's also the cable side too. I mean, they might not coordinate everything, but they'll hire a structural engineer is what they'll do.
And project managers.
Yeah, they might.
A CEO.
Okay, so what we're going to do here, we're going to use those two cases, right? And we just combine them, you just run the numbers and then you combine the cases, such that we got all of these buildings. All right, so WL3 over 6EI, I mean W is the load, L is the length of the beam in inches. Okay, remember that, 6, of course, in E and I, we got E and I up there. And so you can find both the slope and then the delta for both of them. And now the one thing to remember is that tables don't give you the sign, so you often have to be the one who provides that. In this one, it's fairly straightforward. I mean, the thing's bending down, it's curving down and has a negative slope, and it's moving down too. It's got a negative delta, so you just apply the negative signs is really about it. You know, and others, it can get a little bit more complex. So you kind of have to keep an eye on some of those things. So where's the slope? Is the sum of the two. Okay, so I just got negative times the load times the length cubed over 6EI, and then minus the load at the end of the beam, which is 4,000 times the length squared over 2EI. Okay, so that works out to be negative 0.0265 radians, which is about negative 1.52 degrees. All right. And then you just do the same thing for the load. You just use the formulas there, add the two together. The point B is moving down, so you'd want to, you know, have a look at that. Okay, so we're good, and then the downward load, getting about 1.83 inches. So minus WL4 over 8EI minus PL3 over 3EI. Doing all right with that? Any questions? So, you just want to be familiar with the tables, and especially in the English system, the units are really important. Inches and pounds, everything. And remember those distributed loads, because sometimes those are easy to forget because we're so used to pounds per foot. But that would need to change too, okay, to pounds per inch. Okay. Now, there can be more complicated things you can get into with these. So you can do trickier things with the tables than just what I'm showing you here. So that's something I'd like to look at a little bit, is some of the little more complicated things you could get into. And these involve some standard kind of assumptions and just some different ways of approaching things that are used. All right. So let's have a look at this one. This is, my number here is 917. I don't know, I might have changed that number. 910, okay, thanks. So it's changed, 910. All right, so what we have here is a few things going on. We got a couple over there at A, and then we have what we call an overhang, okay? So that isn't simply supported, the beam extends beyond the support. So that's a fairly common condition you might have on buildings if you're doing a porch or something like that. Okay, so here's how you handle an overhang like this. Now the first thing I want to do is find what the moment is about point B, okay? Because I don't have a chart to handle an overhang, I'm going to have to kind of put together a method of doing this, all right? So what I'm going to do, I'm going to figure out how much of a couple does this thing create, all right? So what do I got? I got 4 kilonewtons per meter. That's 4,000 newtons per meter by 3 meters. So what? Is that 12,000 newtons, I think is what that is. And then that's going to have a moment about B, which would be 12,000 newtons times the distance to the centroid, which is 1.5 meters, right? You all okay with that? Okay, so I'm doing that 4,000 newtons times 3 meters, that's the load, times 1.5 meters, so I get 18,000 newton meters, and that's clockwise at B. Okay. So what I'm going to have to do on this thing is consider the angle at B, but also the amount of deflection that's caused by that distributed load on that length of beam from B to C. And then also I got to consider that couple over there at A as well. Okay, so we'll start with that. So we got 18,000 newton meters of a couple at B. Okay. Any questions on that? All right, now let's figure out what that angle would be at B, because the angle at B will affect the deflection at C. So I'll use the word angle and slope kind of synonymously, because again, angle in radians is pretty much equal to the slope for these small angles we're dealing with. All right, now from the charts, what we've got, if you look at that for a simply supported beam, is if you apply a couple at one of the supports or the other, you'll get these results here. The angles are either adjacent to the couple or opposite the couple. Okay. Now the charts show the couple over on the left side. I think I'm not 100% on that. Does it? What's that? Yeah. So that means A there on the left will have a bigger slope than will be on the right, okay? So what's going to happen is wherever you turn that moment in, you're going to get a more dramatic effect on the beam than you will on the opposite side. So don't think of those charts as being in terms of left and right. Think of them in being in terms of adjacent and opposite, okay? Next to the couple and then opposite it. All right, and now let's have a look at that while we've got that one there. Which way would that beam bow if you applied that moment? And everybody just think about this on their own for a second. Would that thing go concave up or concave down if you applied that moment? Okay. Yeah, the one I'm Let's start with that. All right. Now here's how I think about this. I think of taking what I call a T-bar handle. Have you ever seen like a valve wrench? They got T-bars on them. And then I'm going to turn the handle clockwise. If I turn that handle clockwise, which way will that thing bow? Yeah, it's going to go down, okay? But the effect will be more pronounced again next to where the load is. So that thing will bow down pretty dramatically, and then it'll kind of recover and come up like that, will be what it would do. So we're going to have a higher slope, the ML/3EI, next to the load, next to the couple, I should say. And the lower slope, the ML/6EI, opposite where the couple's applied, okay? And that particular one would bow down. You know, and if I have a ruler here, kind of a flexible ruler, I'll apply that clockwise couple on your left. That's it on the right, on the right. That's what's going on. Okay? See how it's more pronounced over by this one? So that's kind of it. And the best way I can think to kind of figure that out is to think of just taking a T-bar and turning it, see what happens. Or maybe bring a flexible ruler with you and do it yourself, whatever works. But, so, okay. All right, so we're going to apply this formula to both of those couples because we got 72,000 on the left, and then on account of that overhang, we got 18,000 on the right. They're both going to affect the slope at B. All right, and we want to figure out what the net effect is. And again, we'll just do it by addition. So why don't you have a look at both of those sketches down there and sketch in what those beams would look like if those couples were applied. So which way are they going to go? Okay, how are they going to bow? And which side is the more has the more dramatic slope? Getting something like that, they both bow up, concave down, the both of them. Okay. The other way to tell is just kind of extend the same direction on the opposite side of the support. That kind of tells you whether the couple is pushing the beam up or not. Here in both cases, if I continue the counterclockwise one on the top, it'll just come around counterclockwise. That'll push that side of the beam up. And the clockwise one on the right will push it up also as it continues around clockwise. So that might be another way to look at it, okay, rather than that T-bar. Okay. All right, and so this is going to be the far side, right? The opposite side. You all good with that? So ML/6EI. And this one's adjacent because we're right next to the couple. So that's ML/3EI. Okay, and from there, it's just a matter of plugging the numbers in. Okay. Now, these answers come out in radians. That's the unit. They're unitless. So, unitless angles are radians. So we want to remember that. It is, yeah, it's a negative slope. So I'm not using the, well, that's a good point. I'm not using the statics moment convention here. I'm just looking at the effect on the slope. And so, from my little sketch I drew, that's going to come down at B. That's going down right, so it's down. Same thing here. So yeah, it's a good point. So don't try and do the static sign convention thing here. I don't think it really works in any sort of systematic way that I know. Anyway. Okay. So we'll just add those together and get the net slope, okay? And again, you just kind of visualize that couple and you should be able to get the direction of those angles if they're negative, okay? Okay, so what we've got there is a negative slope. It's negative 0.00675 radians. That's what's happening at B. Are we good? All right, and then here's that T-bar thing to look at it to get the slopes like we were doing. Okay. All right, so now we've got the total slope there. Now, if there weren't any load beyond B, we could just take the slope, which is and times the x distance, and get the deflection. Okay, if that overhanging beam extended out straight from B, as I'm showing here, to find delta C, you would just take the slope times the distance. And that's a negative slope, so of course that'll get you a negative distance. Okay. Now, from there, if you just take slope times distance, you get the delta y, because what slope is delta y over delta x. So if you multiply that by delta x, how far over you're going, if that slope extends at a straight line, you'll get delta y, which is our delta. Okay. But there's more going on than that. See what we've got that distributed load on that stretch of beam that extends beyond B, and that'll push it down also. So it's not in a straight line, it's actually curving down like a diving board would. Okay. So we have to account for that also. So the first little bit we do to get delta C is just look at slope times that overhang distance. But we got to look at it another way too, and that is considering that distributed load on it. Okay. Now the distributed load affected the slope, which got us that negative 0.00675 times 3. But we also have to consider the sag in the beam on account of that. Okay, so that's going to be from the formula for a cantilever now, because that's the best way we can model this. It's solid material running across B, so it acts like a cantilever. If you ever seen a house with a little porch outside the bedroom, usually they just take those floor joists and just push them out, like on a second-story porch. That's what we're talking about here, and that acts like a cantilever. You just assume that that beam itself provides enough of a support to act like a cantilever. So we're going to use the cantilever side of the formula sheet and use that delta formula for the end of a cantilever, which is WL4 over 80I. So we'll just plug in WL, looks like I forgot to do the fourth power up here, 4 over 80I. And that's negative 0.00253. So the net effect, when you add them together, is negative 0.0223 2.278 meters, which is 2.278 centimeters, just a little bit short of an inch there. Okay, so that's one little trick there. That's the, as far as I know, the standard way to handle these overhangs. Look at the couple they created, their adjacent support. Look at the angle that causes and multiply it by the length of the overhang. And then also look at the effects of whatever load is on the overhang too, as far as how it bends the beam. Okay. So we're good with that? Okay. We're good? All right, now let's have a look at this one again. This is the one we did with calculus. Let's do it with the tables this time. Okay. So we've got this cantilever beam with 40 kilonewtons per meter over just the last 2 meters. Okay, and we want to see what delta C is. And this is that exact problem we did using calculus. This was a full page of calculations and integrals and finding the constants and all that. Let's see how we could do it with the tables. Okay, so what we're going to do here is we don't really have a table that gives us this. If you look at your table for a cantilever, we don't have a table for a cantilever with a load just at the very end. We don't have that. So what we're going to have to do is kind of come up with a way of creating it. So the first thing I'd start with would be a cantilever with a full load of 40,000 newtons per meter on it over that 5 meter span. And to find delta at the end, it'll be WL4 over 80I. So I'll do that first. Okay, and that would get me delta if that cantilever were fully loaded. Now I'll put that negative sign in there because it's going down, so that's what that negative's doing in there. Okay. Yeah, question?
Doesn't it work if you just put the weight at the center like you're doing with the number and use that?
Okay, so the question is, why couldn't we just put the weight, do a single point load right there, essentially? Yeah, it would have, because that would affect the beam differently. This is going to make the beam bend down, but it's also going to curve it throughout the length. If that were just a load at the centroid, it wouldn't deflect the same way. It would curve probably a little bit more dramatically to here, and then it would extend out straight from there. So the shape of those beams are just going to be different. It's not quite as straightforward as you like when you're doing reactions and statics, because we're doing more with it. You know, I mean, the shapes of these curves are going to be very different. So that's the quickest answer I can give you on that. Okay. Okay, so the next thing we're going to want to do here is to figure out how do we account for the lack of this, because that really isn't occurring, right? I've got to take that away. The actual deflection is going to be less than negative 0.1736. Okay, so the way I'm going to do that is I'm going to use a formula for a load over a portion of a cantilever, which you've got on your formula sheet. Wx1 to the 4 over 80I plus Wx1 cubed over 60I. All right, so there's the formula there. Thing bothers me a little bit. Okay, so we'll go ahead and run that. Oh, there, I forgot something on that formula, didn't I? Oh, it's covered up. That's the problem. Okay. Yeah, then I got to multiply it by x2. So that's missing off of that. And that should be on your thing, your handout. There you go. So what I'm going to do then is I'm going to work that out. And there's the numbers on that. So it's Wx1, which is 3 meters for us, to the 4 over 8EI, plus Wx1 to the 3rd over 60I times x2. And what that is, that's a deformation formula plus a slope is what it is. A slope times a distance. And that comes out to be 0.0425 meters. So what's going to happen here is this beam, it's like it's going down 0.1736 meters, but then it's rebounding back up 0.0425 meters. So the net deflection is the negative 0.1311 that we got doing all the angles. Okay. So this is perhaps a quicker way to get to this. We're doing this problem by subtraction. Okay. So that second load there is not pushing it down. It's a load that isn't there on the top case. So this is lacking here. So we're taking it away. We're using the negative of it to remove it and pulling it back is what we're doing. Okay. I'm going to run a couple copies here. I'll be right back. So this is some homework. I think I'll just make this due on the final, and we'll go over it really well in class. What I think I'll do. And then I'll get you a couple more of these deflection ones too. So the ones I'm using today, we could just use the table to work out. Got a couple of tests, so I'll have to get back to these right now. There's that one. There'll be a couple others here. So 411, 413, and 414. Those will be due Tuesday, the 13th. Let's see, let me get this shut down here.